All right, our next topic is going to expand upon our three types of hydrocarbons we have at this point, alkanes, alkenes, alkynes. If we take an alkane and take a hydrogen off the two end carbons, what we call terminal carbons, and leave the one electron on each carbon as the hydrogen takes the other one, and then reattach or newly attach the two ends of the chain into one, we've created a compound that has no beginning and no end. That's called a cyclo compound. Cycle, like cycle, basically called a cycle, a complete repetition of the same thing around. The cycloalkane, of course, means all the carbons have single bonds between them. Cycloalkene is where all the carbons are single bonded except for one carbon-to-carbon double bond. What makes this particularly interesting is that when we put methyl groups on, ethyl groups, and other groups on that we'll talk about later, the naming system becomes a little different, but it's logical based upon what you're going to see. Now, let's take a look at an example of a cycloalkane. This is an example of a cycloalkane. We have here 1, 2, 3, 4, 5. So this is what we call a cyclopentene, or I'm sorry, cyclopentane. Now, if I disconnect pair of electrons, we have two terminal carbons that are not bonded to each other. You'll see that the bond angle is 109.5 degrees for all of this, but this does not really want to go together. You have to add a little energy to force them to become less stable. The most stable of all the cycloalkanes is cyclohexane, because the 109.5 degrees is consistent all the way around. This turns out, if you know your geometry of the pentagon, you know that every angle is 108 degrees. That means we have to put in what we call a little angle strain to get it to fit this structure. The most unstable of the compounds, I guess the best way to put it, is cyclopropane. Cyclopropane, you know a triangle that the angles for a triangle is 60 degrees, yet the angle that is preferable for all the carbon-to-carbon bonds is 109.5 degrees. That is a 49.5 degree strain. And so it doesn't take much for a collision to pop that thing loose. So cyclopropane is really easy to get to disrupt itself when colliding with something else. Cyclohexane, however, enjoys the 109.5 degree bonding that occurs with it. This is cyclopentene. So this cyclohexane prefers the 109.5 degrees. There's no strain involved, so it's a very stable compound and not very likely to react without a little push. Okay, so the more angle strain involved, the more unstable the compound can be. Okay, so let's take a look at some isomers of this thing here. So let's take a look at cyclopentane. Now, this is a representation. Now, we could draw the Lewis dot structure and say it looks like this. We have two hydrogens coming off of this. And as you see, the formula for this is C5H10, which is the same as the alkene formula. But now, because we've attached the two terminal carbons together, it also is going to be for the cycloalkanes. Fits this formula, which is CnH2n. So if I ask for a general formula for a cycloalkane, it's going to be the same as an alkene, all 5 carbons long in this case. Well, you can draw that way. It turns out that you can also draw it this way. Now, so what we're going to do now is we're going to take one of these carbons off. And we're going to reattach the two terminal carbons. Now you can see how the glass is kind of like bulging out. It really does like this. Now we got 90 degrees. That's an angle strain of 19.5 degrees. Not favorable at all, very unstable. But we are going to put a methane on one of the carbons. So we can redraw this. And what we're doing here is we're going to put a CH3 group. That is our methyl group. Now, if this had been a butane, not a cyclobutane, this is a cyclobutane. If it had been a butane and put a methyl group on someplace, then we would have to identify what carbon is it on the first carbon or the second carbon. There are two places that will give you two different isomers. However, there is only one place we can put this. If I rotate that around, it looks like it might be the fourth carbon, that looks like it might be the third. Depends on your perspective of what's beginning, what's ending. And that's the point of the IUPAC naming system, is that nature doesn't care where you start. If there is no terminal carbon, then wherever the methyl group's on is automatically the first carbon if you put another carbon on. And that's not what we're doing, we just have a 1, so we don't have to put a number on the carbon. This is known as methyl cyclobutane. That's the name of this compound, methyl cyclobutane. All one word. IUPAC is all about the big word. However, if I take off another methyl group, and this is where I take a break some of these model structures here. Okay? And I want to try to attach these together. You can see this is really fighting me hard. This is about to bust right here, so I'll do this real quick. But I put this on here like so. Okay? So it looks like this. Looks like this, technically. That's a cyclopropane. And I got a methyl group here and a methyl group here. Now again, if I turn this way, then it looks like it's on the first and third, or the second. There is no place for it to be except on the first and second carbons, no matter what direction you go. You make this 1 and this 2, make this 1 and this 2, but it's going to be, I'm going to take this part to do. I'm about to lose that bond right there. Wow. Okay. You think this is straining plastic? It also strains the molecular hybrid bonds between the carbons, the sigma bonds. I really don't like it. But anyway, when we use the structure right here, you have to understand that every vertex here represents a carbon. And every carbon must have 4 lines. So like right here, this has got 1, 2, 3 lines coming off this vertex. That means the fourth one has a hydrogen on it. This has 3 hydrogens here, this has 3, and this has 3 right here. Okay, this has 3 hydrogens here. This has got 3 lines coming off. I'm sorry, 2 hydrogens here, sorry. Oh, 2, 2, and 2 here, my bad. 2 here because of that. You have 1, 2, 3 lines here, so there's 1 here, 1 hydrogen here, and 1, 2, 3 here. So there's 1 hydrogen coming off here. So 1 hydrogen, 2 hydrogens, 2 hydrogens, 2 hydrogens, 1 hydrogen, 1 hydrogen, 2 hydrogens. Every vertex should have 4 lines coming off it. If it doesn't, then whatever is left over will automatically be hydrogens. In naming this compound, we have 2 methyl groups, and as we saw, it didn't make a difference where we put it. It's going to end up being consecutive carbons that they're on. So we, again, don't need numbers. This is dimethyl cyclopropane. Okay, so let's go to a 6-carbon cyclohexane. Shall we? Now, again, we're going to use this structure right here because it's a lot easier to draw, and we understand at every vertex here to tell you that we have two hydrogens at this point. So this is cyclohexane. Now if I take a methyl group, if I take this and turn it to a cyclopentane, and take one of the carbons as a methyl group and attach it to one of the carbons here, this is what I have. Okay? Now, no matter where I put it, it's going to be on the first carbon by definition, because there's no other carbon to compare to. So we don't need to put a number on it. So this is methyl cyclopentane. Again, remember, one word. Okay, now this is where the fun begins. I'm going to take another carbon out of here. Actually, let's do this. Let's just attach stuff to this right here. This is fine here, and I'm going to do the same thing with the cyclohexane and put a methyl group there, and we're going to call this methyl cyclohexane. I think I'll name my next kid this. It's a great name. Very, very different. It'll definitely give this kid a personality having a name like that. Now, I'm going to attach a second methyl group. This is where the numbering system kicks in. Okay? I'm going to put that methyl group right here, and I'm going to put another methyl group right there. So the question is, what is the name of this compound? Well, now we have to number, because this methyl group could have gone here, this methyl group could have gone here, could have gone here, could have gone here. So let's explore those. Okay? So this is definitely dimethyl cyclohexane. The question is, where do we number this? Well, when we do this, we have to establish a carbon number 1. There's always going to be a beginning point to the attachment. So the number 1 is going to be placed in there. And then IUPAC states that you have to have the lowest possible combination of numbers. So that means the one next to it has to be carbon number 2. We go 1, 2 here, or 1, 2 here. There's 1, 2 hyphen. All one gigantic word. 1, 2 hyphen dimethyl cyclohexane. Okay? Now I'm going to move that. Move this methyl group over here. This is still dimethyl cyclohexane. The question is, what numbers are attached here? Well, we make this number 1, we go 2, 3, 4, 5. Or if we make this number 1, we go 2, 3. If we make this number 1, we go 1, 2, 3, 4, 5, or we go 1, 2, 3. The lowest number in all those scenarios is the combination of 1 and 3. 1, 3 hyphen dimethyl cyclohexane. So as you can see, you want the lowest sum of numbers of attachments in your structure's name.